Section, what did you say it was, 7.3.
Part 2.
We've learned how to do a bunch of different trig integrals. Now we're gonna do trig substitutions to get rid of pesky radical signs. The ones that aren't our basic integrals. We always look for the basic integrals first. Is this a UDU integral? Don't do this trig substitution for a basic UDU integral, you'll waste your time. You'll get the right answer, but time. Make sure you don't have an inverse trig integral already looking at you. That's considered a basic integral. But if you've got a radical sign that you can't get rid of with a UDU substitution and is not an inverse trig function, then we've got these substitutions that will get rid of the radical sign for you. The first one is if you've got a radical sign that's got the quantity, the variable squared behind the minus sign. You take that variable, I've been writing this in terms of x, but I can have an expression in x there as well. Right, when we complete the square, we get an expression in x. So we'll do some completing the square. So I'm going to do it in terms of u today. We take the variable behind the minus sign as the u term. And you know when you have a u, you need a du. You substitute out an x, you need a dx. So in this case, you would take the derivative of u and substitute in a times the cosine of theta d theta. And what will in subsequent steps allow us to get rid of this radical sign is we're going to use the fact that 1 minus sine squared is equal to cosine squared. We'll be able to take these two terms. This guarantees that we'll have a common factor of a squared, so we'll be able to factor it out. The other factor would be a 1 minus sine squared, which we substitute in as a cosine squared. We'll use 1 minus sine squared. Theta is cosine squared of theta. And that's why that one works. Here again, if you have a u, you need a du. If the variable squared is in front of the minus sign, then we use a secant because we have a trig identity that says secant squared of theta minus 1 is a tangent squared. So we'll be able to factor out the common factor of a squared. The other stuff is going to reduce to tangent squared. We'll just have a single term under here and we can take the square root of it. But don't forget the du. D, derivative of secant is secant tangent. So we get a secant theta, tan theta, d theta. If the variable squared is in front of the minus sign, or not, if there's no minus sign, if there's a plus sign, then we take u to be the tangent because we have the trig identity that tangent squared of theta plus 1 is equal to secant squared of theta. And if u is tangent of theta, then du is a times the secant squared of theta d theta. This is our trig substitution to get rid of the sum in there, and we'll end up with just a product. So I'll write it over here, and then I'll put the screen back on the middle board so you guys can see it here. Hopefully this substitution gets rid of the pesky radical sign and gives you a trig integral that you've had enough practice that you know how to do. Here we use the identity that secant squared minus 1 is tangent squared. Here's du, a times the secant squared of theta d theta. And then here, tan squared plus 1. The secant squared of theta. And then remember, once we integrate with respect to the variable theta, we go back and write everything in terms of the original variable. So we'll make a triangle from the original substitution and substitute out the other trig functions. It's a clever substitution, but what makes it fun is that it works almost all the time. The only places that you can mess up is forgetting the du. But you guys won't forget, because I told you not to forget. You need a U substitution, you need a D. Okay, so let me put the little camera to the middle here. Which, how do I do that one? Boom. There it is. Did we work any of these last time?
We did.
We did one.
Oh, sorry, we
did one, so here's another. All right. So let's do one very similar. We'll put an x squared on top, square root sign on the bottom. Last time we did 4 minus x squared or something like that.
Yes.
Let's put a 4 plus x squared here. So I want you to notice as you're writing it down, if there was an x to the first in the numerator and that same denominator, then it's a UDU integral, right? If this were x to the first power here, you take the stuff under the radical to be u, and then the x dx will be part of the du. If there were no radical sign, if I just had x squared over 4 plus x squared, we don't need to do any kind of substitution. We would do what? Divide. When the power on top is the same as the power on the bottom, we do long division and write that as the whole part plus the remainder over the divisor. It's the square root sign that makes it pesky. It's neither a divide problem nor a UDU substitution. So you see the plus sign under the radical sign? That means we're going to go with plus sign substitution. What is the A in our case? So we're going to let x be 2 times the tangent of theta. Now we need a dx, so here it is. Dx is 4 secant squared of theta, d theta. Now we'll go back up there and we'll put all that stuff in.
Is it 4 or 2 secant squared?
2.
Yeah, okay. I was like, is there something I'm missing here?
I'm missing the eraser is what I'm missing.
Right under that.
I don't know where it came from. I gotta make lots of mistakes on Friday. Okay, now we're putting it in. I gotta square the x and put that in the numerator. So I got a 4 tangent squared theta up here. That 4 tangent squared theta will be under the radical sign right here. So I'm gonna have 4 plus 4 tangent squared theta. And now dx is 2 secant squared of theta times d theta. So for this first problem, I'm going to put all the steps in all of their glory. I'm going to go ahead and show you the step where I factor the 4 under the radical sign. Keep that the same. Keep that the same. I didn't even combine the 4 and the 2 because I know I'm going to cancel that 2 later down the line. Because here I'm factoring the 4, and that gives me a 1 plus tangent squared as the other factor. And that's where I said our trig identity comes in. 1 plus tangent squared adds together to give me secant squared. So downstairs I have 4 times secant squared under the radical sign. I can't take the square root of terms in a sum, but I can take the square root of terms in a product. So this denominator becomes 2 times the secant of theta.
you would have showed this to me like the day that we started, I might have walked out.
Dang, I blew my chance. Now we're stuck with you.
Is it secant squared on the bottom?
It's secant
square
squared
root.
here,
Okay.
but that's what made it nice. I've got the product of perfect squares. Yes, sir.
Might be a stupid question,
Great.
but
Do we laugh at you now or later?
just wait a second. You might want to laugh later. It'll make it better.
There's no
So-
laughing allowed in this class.
The secant, does it act like a regular like algebraic function where you can cancel out the exponent? Or is this?
We will.
Okay,
Because secant squared still means secant times secant,
okay.
so I can cancel one of those secants on top, as well as the two. So we cancel 2 secant theta with the 2 secant squared theta, and just leaves us a secant up there next to the tangent squared.
I I'm gonna take my IQ test. Sure.
So let's do cancel in red. That knocks out that, that knocks that down to a 1. Look at that long arm. Could you possibly do that? Could any of you reach down and touch the floor?
I could not. I can go about halfway.
Octopus arms.
Yeah.
He reached down across the desk and put it on the floor.
So what do we have left? 4 tangent squared times secant theta times d theta. All right, so now we gotta think, what was our strategy when we were integrating secants and tangents?
You can change the tan squared into 1 minus, or secant squared minus 1, and then you can also.
Okay,
Or we make a tangent secant.
A lot of tangents and secants, so we'll have to do this.
yeah, we got the problem where none of our basic UDUs are gonna work. Because I've got an odd secant and an even tangent. We like it the other way, an even secant and an odd tangent.
Well, can't we, so the trig identity?
Yeah, we're gonna get a secant cubed. Remember doing the secant cubed integral the other day?
Yes.
That's why I did it. So it's not a basic UDU integral. I can't pull out a secant tangent. Because if I do, I have 1 tangent left and I can't substitute out the 1 tangent. I don't have a secant squared to pull out. So the only thing I'm left with is to go back and replace tangent squared theta with the identity down there. Tangent squared theta is equal to secant squared theta minus 1. So we're gonna make a trig substitution here.
Pull the 4 out.
Pull the 4 out, okay. This becomes secant squared theta minus 1 times the secant of theta d theta. And now multiply it out. We have 2 integrals to do. We have the integral of secant cubed and then the integral of secant.
You split that up into 2 intervals.
We split it up into 2 integrals. This one we do by parts. This one we have a formula for. Do you remember the formula for the integral of the secant?
Plus tangent.
It's the natural log of the secant plus the tangent. Okay, so we're gonna break that up. This one we do an integration by parts. But remember, if I had $1 for every time I do that integration by parts, I'd have $9 by now. You want me to do it again and get $10, or do you want to just look it up in your notes and see what we got last time?
I prefer to look it up.
Let's do it again.
You wanna do it again?
I would like.
See if you can do it again. See if you can integrate secant cubed by parts. It goes circular. See if you can do that without looking at your notes.
But what if we really want to look at our notes?
Yes, that's why you have notes. I just wanted to see if you can do it. If you can replicate what we did the other day.
Yeah, I can't. I'm sorry.
I remember when you were little and you first learned how to do a layup? It's
Yes.
so hard. And then after a while, you can do layups in your sleep. So that's this, integrate secant cube.
In basketball?
Like in basketball.
Oh, okay, just making sure there was something that I was supposed to have learned in math that
No, just math is sports.
that makes sense.
Math is just like sports. It's real clunky when you do it. I always think math is like bowling, right? When you watch somebody else bowl, it looks so darn easy, and then you try it yourself. Ugh, disaster. Don't have enough boardroom to do everything. Another board. Right on here, and erase. Erase, doesn't it? See. Let's see if I write a whole bunch on there. Really not with that score. This is just to keep your cooties off of me. Let me see if I've ruined it yet.
I thought that was one of the ones that you like wrote on and then flipped the camera, like you did the video from behind it.
No, I do this, and I talk to you like this so that your germs don't get on me.
That's what that's for?
Yeah, like Pokemobile.
I thought it was like a full like board. I thought it was like a whiteboard.
I'm gonna use it like a whiteboard right now. I'm gonna integrate Seek and Cube. You guys do it yourself so that you can compare.
I tried, I got like halfway.
Well, you quit. Don't quit.
Okay, I'll quit.
Just switching notes.
God, I hope this doesn't ruin it when it dries.
You can use my deck to probably get it off.
Yeah.
Would I say anything else?
Yeah.
That's great.
Even,
Not anything.
okay, I hope so, because this isn't really glass.
We'll blame Darby. She can find it.
Because she probably still gets an allowance.
Yeah, exactly.
Well, don't have to argue like that today. Like that. Woke up and chose violence.
Can you guys see this? Kind of?
It needs to be like on the solid.
Well, I thought it was. Not solid enough?
What if you just write on math class?
You can see it. It's just the reflection.
Is that glass? No, that is glass. I wonder if I can write on that. Let me do that. Yeah.
You need to just leave it on there. So next, whoever has this class or next walks in is like.
I think I can write on
Yeah,
this.
but like South Shore or whatever.
It's like,
Yeah.
yeah.
So-
You're not supposed to be talking. You're supposed to be integrating Seek and Cube.
Yeah, I did.
Oh, my bad.
You're gonna go Seek and Cube, do that. Write it as a part you can integrate and a part that you can't. I can integrate both parts, but the biggest part I can integrate is the secant squared. I guess I should be using a theta. So then we take the dv to be secant squared of theta, and the u to be the secant of theta.
That made that too complicated.
And so that du is secant theta, tangent theta, d theta. And v, integral of secant squared was tangent. And so this becomes u times v minus the integral of v du. So u times v is secant theta, tangent theta. Minus the integral of v times du. If I multiply v with du, I get a secant theta
Sounds right.
tan squared theta. And that was what we had here. And so we do the same thing again. We replace tangent squared. Tangent squared is secant squared minus 1. So we have secant theta tangent theta minus the integral of secant of theta times, what I say it was, tangent squared is secant squared minus 1.
That's the exact same integral that we had earlier, which means you can cancel without doing any of the hard
Don't you
work.
have a 4 out front too of the original?
That one does. I'll go back and fix that. So I'm going to have a secant cubed of theta. And then I'm going to go ahead and integrate the secant. I got a minus and a minus, and that's going to give me a plus. So in here, I'm going to have my natural log of secant plus tangent. So that comes from this integral. So I add that to the other side, so we get 2 of those. And that gives us secant theta, tan theta, plus the natural log of the secant of theta, plus the tangent of theta. And so the last step is to divide by that 2.
And then we have to solve for that.
Do we have to have the absolute value bars? That is important.
Yeah, probably so. I think Weber will take it without the absolute value bars. Okay, so I'm going to replace this with that. And then I still have that one to go, right?
Which one to go?
This one. So I have 4 times all that stuff over 2. Secant theta, tan theta, plus the natural log of the secant theta, plus the tangent of theta. All of that's over 2. And then minus 4 times that integral. So minus 4 times the natural log of secant of theta plus the tangent of theta.
Hey, look,
Yeah, I'll be able to combine those if you want to. So even though we've done a lot of steps, we're still not done. We've got an antiderivative, but we've got the antiderivative in terms of the other variable. I need to get that antiderivative in terms of the right variable, so I need some more board room, which means I probably have to erase all that over there. Bummer. It looks so good too. You should write that over there. It's too late. Too late. I wrote that over here. And nobody can see it who's zooming.
pretty good.
It's what they get.
Okay, they have it in their notes.
Okay, well, let's simplify this just a wee bit. When this 4 goes in here, it cancels and gives me 2 of these. It's going to give me 2 of those, but I've got minus 4 of those here. So this should simplify to 2 secant theta tangent theta minus 2 times the natural log of secant theta plus the tangent of theta. So I gotta rub this out. Simplifying step, I said we get 2 times secant theta tangent theta. And then again, I've got 2 of the plus natural logs minus 4 of the natural logs to give me minus 2 of those natural logs. Secant theta plus tan theta. And now we're going to get that back in terms of x. Remember how we do that?
You have to undo your initial x
From here.
and then make it, it'll be x over 2 arctan, or x
Okay.
arctan of x.
So that says that tangent of theta is x over 2. And so if we draw a right triangle, we'll be able to figure out what the secant of theta is. So let's identify that as theta. The tangent is opposite over adjacent. And then this should be that, 4 plus x squared. Does that satisfy the Pythagorean theorem? Leg squared plus leg squared is hypotenuse squared? So use that picture and tell me what the secant of theta is.
X squared plus 4/2.
Hypotenuse over adjacent, so you're right. 4 plus x squared over 2. The tangent of theta was x over 2. Let's go in here into the logarithm and do that. Secant of theta was the square root of 4 plus x squared over 2. And then the tangent of theta was x over 2. I got a lot of 2's running around. I can cancel one of these. And we can write our answer as the square root of 4 plus x squared. Looks better to put that x in the front. Now, a lot of times your book will write this like this. I want you to tell me why I can do that. I'm just going to blow off the over 2. How come I can just throw away the over 2's here? The common denominator. So really all of that is over 2. And how do you simplify the natural log of a fraction? Natural log of A over B.
A minus.
Natural log of A over B. There's a log property for that.
A minus.
Natural log of A minus the natural log of B. Well, here, everything's over 2. So somewhere I've got to minus the natural log of 2. Well, that's a constant. So it just gets sucked up in this constant. Okay. So when you see that in your book, you'll think, where'd the 2 go? Well, it's here. The natural log of 2 is in there. But you don't have to. You can leave your answer way up in here. But I do think that there are a lot of problems where web work won't take your answer unless it has the absolute value bars. So these problems are long. That's why I say look for the basic integrals first. If you do this to a basic integral, you'll get the right answer, but it takes up all the room we got. I had to go right on the wall. Okay, so I'm ready to do another one. How about you? All right, my next one. So this would be a basic integral if that were an x to the first power out front. Recognize it? Which integral is that if that's an x to the first power out front? That's an arcsecant. But that x squared is making it more difficult than it's just a plain old arcsecant. The variable squared is in front of the minus sign. So what's our substitution? We need a secant substitution, right? Because we know secant squared minus 1 is tangent squared. So I'm going to replace x with 3 times the secant of theta. And we need a dx, so take the derivative of that. And you get 3, come on, 3, work with me. Secant theta, tan theta, d theta. And we substitute all that in and watch the magic happen. Each x is 3 secant theta. So I gotta square it and get 9 secant squared theta outside, another 9 secant squared theta inside, minus that 9, and the dx I'll put right here is 3 secant theta, tan theta, d theta. So now I have limited boardroom, so I'm not gonna do all the steps in their glory. I'm gonna just scribble them right here. Here I would factor out the 9, leaving me with a secant squared theta minus 1. Then secant squared theta minus 1 is tangent squared. So that stuff under the radical becomes 9 times the tangent squared of theta. So I take the square root of that, and it becomes 3 tan theta. So in the next step, I'm going to rewrite that problem, take the radical sign out, and put in 3 tangent of theta. I still have the numerator the same. Nine secant squared is still there. But now replace that square root with 3 times the tangent of theta. With me? So cancel, cancel, cancel. We can knock out the 3, the tangent theta, and one of the secants of theta. I've lost my integral sign. Let's squeeze it in there. It look naked. Eek! There we go. So what's left after you cancel everything?
1 over 9 secant squared.
1 over 9. Can I pull the 1 over 9 up front?
1 over 9 secant.
It's just a secant because one of the secants cancel. Is that bad?
Just cosine theta.
That's just cosine theta, right? 1 over secant is cosine. Everybody and his dog can integrate cosine. If your dog can't integrate cosine, then he's just a mutt. And our cosine is sine. We have 1/9 sine of theta.
I was writing extra tiny for this one, expecting it to be really long.
Then we have to go back.
Then we go back to the original substitution. To this one, I can rub out those words next to it and do it right here. I'm gonna do it right there. Okay, so I'm going right back here. That says x over 3 is equal to the secant of theta. And we want to be able to get the sine of theta, so let's go ahead and draw the triangle. Secant is hypotenuse over adjacent. So I can replace the hypotenuse with x, the adjacent with 3.
And then it's
This squared plus that squared is that squared. It always ends up to be this term. Put it in there and make a quick check. Leg squared plus leg squared is hypotenuse squared. So that one does work here. And then the sign is opposite
Opposite
over
hypotenuse.
hypotenuse. Opposite over hypotenuse. So our final answer is 1/9. Opposite side is the square root. X squared minus 9. The hypotenuse is x. That wasn't too bad, was it? That was fit on one board.
It's interesting that you can use this sine and cosine to get all the mess done, and then you can sometimes escape it altogether. Never mind. It's just interesting that you get from the x squared minus 9 back to the x squared minus 9.
Oh, yeah, well, it should. I mean, think about what happens if you were to take the derivative of this, right? The derivative of a square root is 1/2 times the square root. So it's gonna put it in the bottom. Right, an antiderivative. If I take the derivative of this, I should be able to simplify it to that.
And then the x is gonna go up with x.
Find it?
Yes.
Okay. Okay. I got more. Let's see, here's my next one. Got a radical sign downstairs. X squared plus 8x plus 25. It's all under the radical sign. It's kind of different from what we've been doing. We don't have an x squared minus a squared minus x squared, or a squared plus x squared.
Oh, we got three.
I got this guy here.
The square.
Oh, we complete the square, and then we have x be the whole.
Complete the square, right? In our forms, we don't have an x to the first power term. So you're going to complete the square. Try to complete the square at the step under the radical form and see if it fits any of the forms we have. Complete the square. Purple's awfully light, nobody can see that.
So do we first U sub and then we do the sine sub or whatever? The upper one end up being.
Yeah, you can do it in several steps. Or if you've got, say, an x plus 3 all squared, you can just say let x plus 3 be whatever.
Oh, okay.
It's up to you. All right, so let's see. I put my x terms together, scoot the 25 over, add a number here, I take it out here. What did you guys add?
16.
Half of 8 is 4, 4 squared is 16. And take it out. And then you should be able to factor x squared plus 8x plus 16,
Plus 4.
x plus 4 all squared. Last two numbers add to 9. Then we've got 1 over the square root x plus 4 squared plus 9. And now it looks more like that one. You got a plus sign between the stuff. So if you wanted to formally change the x plus 4 to u and the dx to du, you can. I'm just gonna skip that step and say, let's let x plus 4 equal 3 times the tangent of theta. Is that okay? But then the derivative of the left-hand side, we'll simplify to just dx, right? The right-hand side has as its derivative 9 secant squared theta d theta.
Or just 3.
I don't know why I have 9. Why do I keep squaring that number? I'm going one step ahead. It's a 3. All right, now put it in. When you put it in, it will become a product under there. Let's see what happens. How far you can simplify the integral in terms of these trig functions. Look at how far this simplifies. Just simplified to the integral of secant. Did you guys get it simplified to the integral of secant? I
Yep.
did. Hoorah. Yeah. Let's see here. Dx is 3 secant squared theta d theta. X plus 4 is 3 tan theta, so when I square that, I get 9 tan squared theta plus 9.
Oh, that's why I messed up.
All right, I think I got room to do the factoring right here. Factor out the 9 and get tangent squared plus 1. And then in the next step, replace tangent squared plus 1 with secant squared. I kind of like putting that step in because that's the rewarding step. You get a sum written as a product. And so I can take the square root and get 3 secant theta down there. Threes cancel, one of the secants cancel, leaving me a secant on top. Told you we'd be doing that integral a lot. Natural log of secant plus tangent. All right, let's go back then. We're going to go to here and say that the tangent of theta is x plus 4 over 3. So that tangent of theta is going to be replaced by that. That represents the opposite over the adjacent. Let's put an angle theta here so that its opposite is x plus 4 and its adjacent is 3. What's going to go here?
Root of x squared plus 25.
Yeah, you can either write it like that or you can write it like that. So it'll be x plus 4 all squared plus 9. Then the secant is hypotenuse over adjacent. So in here, we'll have the natural log of the hypotenuse, x squared plus 4, nope, x plus 4, all squared, plus 9 over adjacent is 3. Tangent was x plus 4 over 3 plus c. And if you want to leave the over 3's out again, you can. Since it's a common denominator, you can write that as the log of the top minus the log of the bottom. Log of the bottom is a constant, and so it can get replaced by a new constant. Pretty cool, huh? Now what am I gonna do with the rest of the time?
It's Friday.
We could take naps.
You can take a nap. Yeah, why don't we get a pizza? I like that idea.
We should have a math.
Who's the person who's supposed to say, well, why don't we do another one?
What if we calculate the area of the pizza and we count as them?
What if we slice the pizza into infinite rectangles and we eat it that way?
No, you have to slice it into little pie slices because it's like arcing, you know?
Yeah.
That's not a bad question. What if we went over homework in there?
That's a great use of our time. Keep cutting the pieces until it's.
One of your homework problems looks like this. And here's one similar to your homework and similar to this.
Are we gonna race the whole, like, let's clear the whole board up.
I guess we have to do the pizza party at 11:50.
Hey man, who wants to call a pizza to you? We all in there.
Pizza University.
I'll let you run it out and grab it. Okay.
All right, so this one we're doing next. Again, you see the presence of the x to the first power, but you'll always look to see, is this an easier integral to do if I just did a u du? But I don't have anything that would be a du term. So it can't be a u du integral. But the presence of the x to the first term with the x squared term means you're probably going to have to complete the square. And you gotta be careful because you're completing the square with a minus sign on the x squared. So let's see if you can do it. Because last time I did that, I blew a sign. Another complete square integral. You can have homework put up on this yet?
Yes, let's do this side. Yeah.
Why do I do that? Right over here. Why did I give you 2 monitors when you can't use 2 monitors? I'm kind of curious how you complete the square on this.
Is it -1 or +1?
Add it back in.
Question, isn't it?
Yep. So then write it as 1 minus x minus 1 squared. Let's see what you got. No, because that's gonna, because it, oh yeah, if you take those parentheses away, that does do the right thing. Now does it factor for you? Because 1 squared is 1.
I'm stupid.
1 minus x. 1 minus x minus 1 squared.
Factor out the -1 of everything,
What'd you get?
and maybe it will factor for you, so that you have a lead term of x squared. Yeah, that'll work. So maybe write it in the other order so that it has the general form of the quantity squared is behind the minus sign.
Okay.
Square completed? Perfect. Perfect. Let me get caught up with you all then. Okay, so let me complete the square and see if this is kind of how you did it. Let's see, if you just pull out a -1 here, we'll put it back in later. So that it'll be an x squared minus 2x, then I add something and I take it out. So half the 2 is 1, 1 squared is 1. So I add a 1 and I take out a 1. The first 3 then will factor. Got a minus here, so it factors as x minus 1 all squared. And then I have a -1. And now's where I put this back in. So you have a minus x minus 1 squared plus 1, which we're going to write in the other order. And whether you have this as x minus 1 squared or 1 minus x squared, it doesn't matter. I'll give you the same thing. So that now is going to be under that radical sign. Questions on that, anybody? So I kind of like to get the minus sign out of the way to complete the square and then put it back in on the end. That way I won't make as many mistakes. So which of these does that look most like?
Sine theta.
The variable is behind the minus sign, so we will replace that stuff in the parentheses with the sign of theta. So our next step is to let x minus 1 be the sign of theta. So the derivative on the left gives me dx, the derivative on the right gives us cosine theta, d theta. So keep going, see what kind of integral you get in terms of trig. I'll do the cosine squared integral to integrate? No, yes? Remember how to integrate cosine squared? Theta over 2 plus the sine of 2 theta over 4. Having the sine of 2 theta in your answer is a little bit of a problem. And remember a double angle formula for the sine? 2 sine theta cosine theta. Those are good. All right, well, x minus 1 is the sine of theta, so this becomes 1 minus sine squared of theta. Dx is cosine theta d theta. 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. The product of 2 cosines is a cosine squared. Okay, so that was what? Theta over 2 plus sine of 2 theta over 4. But our triangle is going to have angle theta, not angle 2 theta. So that's where the double angle formula comes in. So I'm going to go ahead and replace it with 2 sine 1 theta, cosine theta, d theta. Oh, not d theta. Okay, that's the trig identity right here. And then you can also cancel here to here. Pull out the common factor of a half. Now let's write our final answer. What am I going to put in for theta?
The arc sine of x minus 1.
Do I see that? The theta is the inverse sine of x minus 1. And then we got the cosine theta to worry about, so I can draw the triangle that the sine of angle theta is opposite over hypotenuse. So I can put an x minus 1 here and a 1 there. And then the other leg should be the square root of 1 minus x minus 1 squared. So our final answer is, I pulled the halves out. So theta is the arcsine of x minus 1. And then I have plus the sine of theta. First row says sine of theta is x minus 1. Cosine theta is adjacent over the hypotenuse. Our hypotenuse is 1, so we don't need to worry about that. So we just put our adjacent side in here, which is 1 minus x minus 1 squared. So you have a web work that's almost identical to that. Maybe your 2 is a 4 or something else. Okay. Any questions? You kind of like this stuff?
I like it. I like this section.
It's more fun when you do it. You'll see, it's much more fun when you do it than when you try to write what I'm writing. Okay, so I guess if we've got 15 minutes left, why don't we just add some fractions together? Quick, what's 1/2 plus 1/3? 5/6? How'd you do that so fast?
Because that's just something that we memorize.
Half is the same as 3/6. A third is 2/6. 3/6 plus 2/6 is 5/6. Good. Now I want you to add 1 over x minus 1 with 1 over x plus 2.
So that's,
You're gonna multiply.
okay, wait, so that's x minus
Rewrite it up
one
here.
Here, a single
Two
thing she said.
over the,
I was too busy saying we should do math flashcards or online.
I could see it in my head. I just figure out the numbers were, but like you do the.
yeah. So it's.
Add those two fractions together. But I'm not kidding. This is what we're doing next.
2x plus
Is this
1 over
7.4?
x
This is
squared.
going to be 7.4.
That's good.
This is the basis of 7.4. When you add two fractions together with different denominators, you get a common denominator. So I'm multiplying the first fraction by x plus 2 over x plus 2, the second fraction by x minus 1 over x minus 1.
Wait, is this 7.4 now?
It will be.
Okay.
It's motivation of what we're going to do in 7.4. Do you want it labeled because you're just a type A kind of guy? Well, I'm going to label it. Section 7.4, we're going to add fractions together. But we're going to do it backwards. We're going to have what the two fractions added to, and you're going to come up with the two fractions that we added to get that, or more fractions.
This is decomposition.
This is deep, we're combining, we're making the composition, then we're gonna do a decomposition. So now they have the common denominator. I can write the common denominator down here. And then the numerators will simplify to x plus 2 plus x minus 1. So my numerator simplified to 2x plus 1 divided by x plus 2, x minus 1. So our task in this section, you're going to be asked to integrate something like that. And you think, oh, I can't integrate something like that. I accidentally put one of those on web work. And you got a fraction that we couldn't integrate, so I had to take it off because we hadn't covered that yet. But the trick in integrating a fraction like that is to realize that this came from adding two simpler fractions together. So to integrate this, you just integrate that. That's the natural log of x minus 1. That's the natural log of x plus 2. So we've got to learn, how do I take a fraction like that and figure out which two fractions were added to get this one?
It's not too bad when the numerator's 1.
Yeah, well, I could have done the same thing and made the new, put a 4 here and put something else there.
It's more annoying.
It's not annoying.
It's
It's annoying.
I don't remember doing
I mean, the radicals are pesky. So that.
So we go from pesky to annoying?
how about tedium?
All right, so I'm gonna see if you can do a similar problem, but backwards. Okay, so what fractions? Find the fractions that were added.
Just my arm on my key.
Get
What am I supposed to ask? How are you?
Outstanding.
How are you doing?
I feel like that was a microtransaction.
No, I can't ask if you're okay, so I need to. Oh, wait, sorry, I need to make sure my voice is going. How are you doing?
Okay. So I've given you a fraction and I said, well, this came from adding some fractions together. Is it possible that the fractions I added together looked like something over x plus 2 plus something over x minus 10?
Most likely not.
Absolutely not. Because if I add a something over x plus 2 with a something over x minus 10, my common denominator is going to be x plus 2 times x minus 10, not x plus 3 times x plus 5. So I bet you $1 I added a something over x plus 3 with a something over x plus 5. Because that's the only way that's the common denominator. I know that because my fraction's in reduced form. How can you tell if a fraction's in reduced form? Yeah, the degree on top is smaller than the degree on the bottom, and there are no common factors from the degree on top to the bottom. So I know this had to come from adding an x plus 3 with a something over x plus 5. All I need to do now is figure out what somethings were on top. So got that factored into 2 prime factors. And I just got to figure out what goes on top. Is it possible that I had like an x squared plus 4x plus 9 on top of one of these fractions?
No.
If the fraction that I start with is in reduced form, then I added fractions of in reduced form. So if I am adding fractions in reduced form, then they can't have any x's on the top. They have to have just constants on the top. So I don't know what they are, so I'm going to stick some unknowns there and solve for them. I grab a couple of variables. I'm going to find the values of a and b. Just by doing this, I'm going to get a common denominator and do it in terms of a and b and figure out what a and b have to be. So just do all these steps where an a and a b is here. I'm going to have to multiply this by x plus 5 over x plus 5. I'm going to multiply that by x plus 3 over x plus 3. And now they have the common denominator, so I can write them as a single fraction. I can expand the stuff on top. Here's that common denominator. On top, I get ax plus 5a plus bx plus 3b. And I need that to look like this. I need that to look like 4x plus 6 over x plus 3 over x plus 5. So that numerator over there has to be this numerator over here.
One of them has to be negative.
So 4x plus 6 has to be this numerator. But I'm going to put my x's together and factor out the x. And then I'm gonna put my constant terms together. So something times x plus something has to be something times x plus something. That means the a plus b has to add to 4, and the 5a plus 3b has to add to 6. So a plus b has to be 4 because the x coefficients have to match. And then the constant terms have to match. 6 over here has to be the 5a plus 3b there. Are you with me? All right, we have 2 equations and 2 unknowns.
Solve for one and
Solve for one,
substitute it.
substitute the other. So how about we say that b is 4 minus a? Put that in where the b is. So I have 5a plus 3 times 4 minus a is equal to 6. Let's take that and solve it for b. So 5a plus 12 minus 3a is 6. Let's see, 2a plus 12 is 6. So how about I write 2a is negative 6? And a is then negative 3. Truly amazing that I just made this problem up off the top of my head and we got a whole number answer. I expected a to be 57 over 12. All right, if a is negative 3, what's b? A is negative 3, b has to be 7. Feed that back up in here, and it gives you that b is equal to 7. So there's our answer. This came from adding minus 3 over x plus 3 with 7 over x plus 5. And the reason that that's good is because if I want to integrate 4x plus 6 divided by x plus 3, x plus 5, then I just integrate that plus that. They both have a plain old x to the first power in the denominator. So it looks like a minus 3 over u du, 7 over w dw. They're both natural logs without any additional constants that I need to factor out. Then we get minus 3 times the natural log of x plus 3 plus 7 times the natural log of x plus 5. So that's the easiest example. This is called partial fraction decomposition.
Will this eventually incorporate like signs and stuff like that?
It can with some substitutions, but it's generally a technique to integrate a polynomial divided by a polynomial. It's not a UDU substitution. So we're going to use this to try to integrate some polynomial over another polynomial. Right? No radical signs. Where this is going to be in reduced form so that the degree on top is smaller than the degree on the bottom. And we can do some factoring to this thing here. So we write the denominator in completely factored form, and then we have to try to guess, an educated guess, what factors were added to get that fraction. Now, when you have distinct first degree factors, guessing's easy. However many different first degree factors here, I make a fraction with each of those factors there. And the numerator always has to be 1 degree less because I've got to have things in reduced form. But now, tell me what the common denominator is when you add, tell me what the least common denominator is when you add 1/4 with 1/6. What's the least common denominator?
12.
12, right? But I could get a 1/4 by adding a half with a fourth, can't I? Right, a half with a negative 3/4 will give me a 1/4, be a negative 1/4, but it'll be a 1/4. And I can get a 1/6 by adding a half with a third. So the problem is if you've got things that aren't prime, that have other factors in them. So for instance, if I had that, it's possible that I added a 1/x-1, a 1/x+2, but it's also possible that there's a third factor, a something over x-1 squared. Don't they all have the same common denominator? So all possible denominators that add to these would be that one, and then one more with that square. That will be called our repeated factor rule. If I have something here that's second degree, then it's possible that my numerator of the reduced fraction might have an x on top. So I wouldn't guess if I had a second degree here, I gotta put a first degree factor on top. Because that's still in reduced form. It's a possible fraction that was added to that one to get that one. Right, so we're gonna have, if we have a prime factor down here that's second degree, we guess a first degree numerator, and it throws more unknowns into the game. The more unknowns, the more work here. However many unknowns you have to have the number of equations. So this can get messy after a while. We'll do the messy cases on Monday because nobody does messy cases on Friday. Gone, people be gone. I'll throw a new one.
All right, everybody, Dion at 12:15, right?
The thing that's happening today,
Yeah.
isn't it like definitely an interesting speaker?
I have no idea who it is. I just.
Isn't it social?